Fabiana?
Yes, I am ready.
Already
okay. Okay, I see. Now I share my screen.
I'm admitting everyone. Danuta,
Yes,
I think is
sure.
not yet here, but
Okay.
hopefully this will now be solved. It seems that only Danuta is still not here.
Okay.
So thank you for your patience, and
Yeah, sure. Don't worry.
Sorry once more for these
Sure.
technical issues.
Okay.
I think, I don't know, perhaps you can start. I don't know what. Danuta is. Danuta? Danuta?
She's not here.
Your Sorry, Fabiana, Danuta has problems now with her connection. I apologize. So could you be so kind and start your presentation? She will join
I start my presentation. Yes. Okay.
Sorry, thank you.
Don't worry. Okay. So let us start again the presentation. This is as a non-conventional modeling techniques, because they are based on the solution and on techniques for the solution of inverse ill-posed problems. And they focus on the use and the introduction of an automatic way to set the regularization parameters using a uniform penalty principle. And so we will see in detail what it is. So this presentation has two parts. In the first part, I will introduce the general concept about what we mean by balancing and uniform penalty principles and how we introduce them into the modeling of NMR relaxation data in general. And I will end by giving a general computational framework that has details depending on the specific relaxation problem that we want to model. And in the second part, Dr. Spinelli will show the details about two softwares, the last softwares that we developed to solve to model problems in the context of fast field cycling inversion data and two-dimensional relaxation data. So let me start with a common example that is it is a general framework in which we can represent the inversion of a general NMR data as the solution of an integral equation. This equation is a Fredholm integral equation. The kernel of this equation, which is this decaying exponential function, is usually a continuous and functional way to represent what it is discretized as a linear system of equations. This linear system of equation contains the discretization of this kernel. In this case, we see this decaying exponential function, and in general, in other types of NMR relaxation problems, we might have a different type of kernel, but the fact that we have anyway regular functions or sufficient regular function to define this integral equation gives us the ill-posed nature of these problems, in the sense that when we want to discretize this problem and we try to solve this problem from a discrete point of view, what we obtain is a matrix that has characteristic behavior, characteristic ill-conditioned behavior. So in general, I focus on this first example because it is quite simple, but we will repeat the same principle with a different type of kernel, such that, for example, given by Lorentz, linear combination of Lorentzian functions, so for example, a Lorentz kernel. So what we have is a measured signal. Here we have the contribution of this model and the contribution of noise, because usually data are acquired with noise. So when we discretize this problem, we have this system of linear equation. K is the discretization of the kernel, and E is the discretization of noise. So usually we solve this problem by, for example, a least square fit. This is the most natural way to solve this problem. In this least square fit, we consider the solution at the unknown relaxation time distribution, or whatever function we need to represent our problem, into a space which is which can include, for example, constraints. So we have this subset of Rn of this space in Rn, and this subspace can contain, for example, positivity constraints or bound constraints. So in general, we end up with a discrete bounded least square problem. This is in the most simple way. So we have that this problem is, as I told, a nil condition problem. And before we consider and we see why we introduce a regularization approach, we have a simple way. In this case, we have a linear model, and so we have a simple way to analyze the conditioning. And this simple way is obtained by using the singular value decomposition. Singular values decomposition is consists of the expressing of this matrix as a product of three matrices. The U and V are orthogonal matrices, in the sense that the columns are orthogonal, and S is a diagonal matrix. The diagonal elements of this matrix S are named as singular values, and we have a way to compute these singular values in such that they are ordered from the greatest to the smallest. The properties of this singular value is that they are real, all real numbers, positive or zero numbers. And usually when we compute the singular value decomposition of every matrix, this is a property that holds for every matrix, we have a spectrum somehow. This singular value spectrum gives us the contribution of positive values up to a number R, which is the last value, which is positive. This R is related to the rank of the matrix. And so when we have problems, when we usually compute the singular value decomposition of the matrix, we have only R values, or R singular values that are positive, different from zero, and the other ones that are zero. This gives us the contribution of the rank of the matrix. and allow us to define the condition number. We have this condition number, let us define this in a particular L2 norm, which has the ratio between the largest and the smallest non-zero singular values. This is the conditioning of the matrix. Moreover, with this decomposition, we can just express the solution of our least square problem as a linear combination of the column of the matrix V, so the singular vector, the right singular vectors that are the elements of the matrix V, times this number. This number is a weight, and this is also named as the Fourier coefficient of this decomposition, in which we have the scalar product of the left singular vectors times the data over the singular values. This is the classical way in which we can solve a linear least square problem. So of course, due to the dimensionality, we cannot always use this decomposition from a practical point of view. But anyway, if we have a small problem, we can analyze. We can write the solution and also have as a contribution the condition number of this matrix. Now, when we apply this idea to our, for example, matrix coming from the simple multi-exponential decay of our model, what we obtain is an ill-conditioned matrix. Matrix K is ill-conditioned, and we have what we have is that the matrix conditioning is very large. So what we have is a great ratio between the largest and the smallest singular value. But the reason because of this large condition number is due to the fact that we have a very small value in the smallest singular value decomposition. We have this sigma r is very small, and this gives characteristic difficulty in the solution of these least square problems, especially when we have noisy data, because you see from this decomposition, this part of the decomposition, that when S is corrupted by noise, this noise has as a denominator this function sigma I, and so the contribution from the smallest singular value end up with amplifying the contribution of noise. This is what we know from the classical solution. And this is an example where we consider the matrix with a simple exponential decay contribution. This is an example where we have the times, the times and the correlation times in the range that is typical for example, NMR data. In this case, we have, as you can see, this condition number, which is very large. But the interesting thing is the way in which the singular values decay. Because this decay, which is, let us say, almost a log uniform decay up to a value which is close to the precision, machine precision, causes an explosion in the coefficient. This is what are the coefficient of our linear combination. And when this coefficient weight the noise, cause an amplification of the error. And this is the behavior of the relative error for the introduction of the different coefficients. So if we go back here, we can measure the error from the different value of I, which means we have we are constructed our solution by including more and more terms. And so what we expect is that the error decays, but when we reach a critical value, and this critical value depends much on the problem, so it is unknown, then we have a steep increase of the error. And this is the reason why we cannot afford the solution in the, let us say, classical sense. We have to do something to avoid this increase of the solution. And this is just an example, but in different way. It happens every time we solve an nil-post problem. So now I move to a more general representation of the problem. In all our problems, in our NMR models, but in general, in our models, we have measurement data. We have a set of parameters, and what we want to do is to find the parameters in such a way that our data fit somehow our model. So this P of x theta is our model, which can be linear, as in the example that I show you, or it can be a general nonlinear problem. And so what we do is we solve a possibly nonlinear least square fit, for example, fitting problem. Here we might introduce weights that are useful in many situations, in many real situations. And what we have is that the identification of the parameters that constitute our model is a linear or non-linear, depending on the model, ill-post problem. So we have the same behavior. And so we cannot think of using our classical solvers also for nonlinearly squared problems because of the presence of noise and because the solution in this classical sense gives us a solution that are dominated by noise. So in general, what we have is that a classical solution might not exist, is not unique, but we are in this situation. This classical solution does not depend continuously on data, and so what we have is that the noise present in the data let us dominate the solution and make the solution actually useless. So we apply a regularization approach. In our softwares, let us say, we introduce regularization parameters, so we have the possibility to introduce more regularization functions. So we have a linear combination of regularization parameters and the regularization function. The idea of all these functions is to somehow damp the effect of the presence of noise or avoid that the presence of ill condition spoils and dominates the solution. Of course, the different types of regularization depend much on the problem and on the property that we want to see in our regularized solution. Moreover, we introduce physical bounds. They are important because many of these problems, in many cases, especially when we have nonlinear least squares problem, we have non-unique solution, and it is very important to set the bounds, the physical bounds of our problem. Otherwise, we might find minima that are not sensible to our data. So let us say which kind of regularization function we have we used in our softwares. First of all, we define, we have two possibilities. We can have a multi-penalty regularization, which means that we have more functions. This is an example of two regularization functions. The classical example of multi-penalty regularization is what is named as elastic neck regularization. We have an L1 and L2 norms of the, in this case, parameters, our solution. And so we have the linear or nonlinear least square combined with the contribution of two regularization functions. This is one approach. The other approach is a pointwise penalty. When we want to penalize the contribution for every different point. So for every value of this regularization function, we have a different regularization weight. So what you see here is that in this case, we have number of points. So P is equal to the number of components of our parameters in this case, and we have a linear combination of these parameters. So in both cases, the problem is to find the regularization parameters, to set the regularization parameter in an automatic way, because when we have more than one, or as in this case, we have as many regularization parameters as the dimensionality of the problem, it becomes vital to have the possibility to set them automatically. And for this reason, we focus on two principles. The general principle is the idea of weighting, of balancing the weight between the regularization part, and what we see here is a general function. This should be, as I say, this could be, if we consider R as a vector, we might think this as a scalar product. This is the scalar product of all the regularization parameters. And the residual, let us say, this residual also weight is an approximation of the noise. And we have two strategies. Basically, historically, there is an historical paper from Ito and his collaborators in the framework of the solution of inverse problems, which developed also the theory for the balancing principle. The balancing principle says that we can basically balance the weight of the regularization part, of the residual and the regularization part, provided that it is positive, is given different from zero. Depending on the parameter, this parameter gamma is unknown. So this parameter gamma depends on the problem, and they don't give actually a way to define this parameter. And but anyway, for each value of this parameter, positivity parameter, they develop a theory, a convergent theory for this balancing principle. What we see here is something which is very close, but it is related, but it is not exactly equal, which is the uniform penalty principle. The idea is still to balance the contribution of the residual to the contribution of the regularization part, but we admit that our regularization parameter depend on the number of the regularization terms. So this gamma is not present anymore. And this R tilde is related to the type of regularization, but it is related to different features. So we introduce a modification of the regularization function that allows us to to improve much the quality of the result. Also for this, there's been developed, we are developing also a convergent theory, but it is not interesting in this context. So given this is the general framework, starting from the 2000s, this uniform penalty principle has been introduced for the one-dimensional data inversion. And this is just a way to show you in what I mean when I say that we have this function R tilde. This is our function R tilde, and this function R tilde is different from the function R. The function R is, in this case, is simply the function theta I plus 1 minus 2 theta I plus theta I minus 1. So this is the regularization parameter and regularization function that contains this part, but here we have a modification, and this case rise to a software package, which is UPenWin, which has been distributed in 2008 for the solution of one-dimensional NMR inversion data. Then it has been extended to two-dimension, and this extension to two-dimension gives a different software, which is the 2D uniform penalty software, which is at the origin of the most recent extension. In this case, we introduce also a regularization in the L1 norm. So here we have a multi-point-wise regularization, and Dr. Spinelli will show you the details about this software. Finally, the most recent contribution is the application of this principle to our, for example, FFC data, where we have a nonlinear, the combination of linear and nonlinear model. So we have a nonlinear model that has a linear and nonlinear part inside, and we use a pointwise regularization. We use multi-penalty regularization. So this is the final, so somehow the history of the different softwares, and Dr. Spinelli will show you the details. So in general, every software has this frame of this great scheme. If we like, we have the data, we have to choose the regularization parameters. The initial regularization parameter, many times it is equal to 1. We start with a classical value. Consider that this lambda is a vector. So what we solve at each, we have a loop. Inside each loop, we have an approximation of this approximate parameters. We update the components of the regularization parameters using our uniform penalty principle, and we are able to stop using this stopping rule, which means that we are claiming that there is a convergent behavior, and there is, but of course the mathematical theory behind it is more complex. But there is a converging behavior, so we can actually stop when the discrepancy between the solution, the approximate regularization parameter is smaller than a given tolerance. So this is the general framework that I wanted to use, and is the end of the first part. And now I leave to the second part, where Dr. Spinelli will show you the details, the 2 examples of the implementation of this general principle. So I can stop here. If there are questions, I can answer. Otherwise, I will leave the continuation to Dr. Spinelli.
Do you have any questions about the concept? You see, we have really interdisciplinary team here. Yeah, but this is really very nice. Imagine this is true. From really a kind of advanced mathematics to food science, and this is what we really do. Fabiana, I think that that we could move to demonstrating the software.
Okay.
Okay.
So yes.
Good morning. I'm Giovanni Vito Spinelli.
So let me stop sharing the screen, because otherwise. Okay, and maybe Gianvito, you can start to share your screen.
Yes. Okay. I'm having some problems with the camera of my computer, so if it's not a problem, I will do without the camera presentation.
No problem.
Sure.
I will start to share my screen. Okay. I'm having some problems because
I'm not able to stop sharing.
You cannot start.
I cannot stop sharing. This is the problem. I don't know how to do this. Let me see if no, sorry. Maybe I exit from this part, so you should. Okay.
Now we'll try. Okay, yes, I can.
Okay, it seems not. Okay, we see your screen.
Can you? Okay, perfect.
Yes.
Okay, good morning to everyone. I'm Giovanni Vito Spinelli, a PhD student in mathematics at the University of Bologna. And during this continuation of this presentation, I will show you the 2 softwares that we developed to model this NMR relaxation data. So these 2 software are based on the numerical methods and the mathematical models that Professor Zama told you previously. So the first software is called Model-Free FFC, and it was developed to fit nuclear magnetic relaxation dispersion curves obtained by fast field cycling measurement. Fast field cycling experiment is a non-destructive low field NMR technique that allows to reveal information about the molecular dynamics of the sample under examination. The technique consists in rapidly changing the intensity of the polarizing magnetic field B0 and acquiring the relaxation. Sorry. Okay. So the technique consists in rapidly changing the intensity of this magnetic field, the polarizing magnetic field, and acquiring the relaxation rate, R1, as a function of the Larmor angular frequency. In this figure, it is shown an example of this relaxation rate. And this rate can be represented as a linear combination of spectral density functions of the motion, modulating the interactions. But in complex systems, the evolution can might present some local peaks, some local maxima. And this could be, these are due to resonant phenomena, and could represent a difficult thing to fit in with our software. So we started using a model for this kind of data. The model is the mathematical model is called model-free approach, and where R1, so the acquired longitudinal relaxation rate, is a sum of three terms, a constant offset greater or equal than 0, R0, and this takes into account very fast correlation times. A linear term, RHH, which describes the longitudinal relaxation rate, and it is given by this integral, and it depends on this f of tau c, which is the correlation time distribution. And in case of presence of this local maxima, this effect is called quadrupolar relaxation enhancement. There is also this nonlinear term, RNH, which describes this effect, and it depends on 6 physical parameters, which are here in blue. So the idea is that with the software, we want to fit, starting from the experimental data, we want to fit the profile and extract these parameters of interest as the constant offset, this correlation time distribution, f of tau c, which has this shape, the function, and the 6 parameters of the quadrupolar effect, in case it is present. So the first thing with the software is to discretize the problem, and we start from the observation vector y, and we have a discretization of the f of the linear part, so the RHH, the integral, with the function f1, which is given by this product by the matrix K and the f that we want to extract, and which has this this equation, the K with the kernel, and the discretization of the quadrupolar part, which is given by this other equation. And okay, to solve the problem, to extract the parameters of interest, we reformulated the problem as the L1 regularized nonlinear least square problem. So we want to solve this minimum problem with the regularization term at the end. And of course, this is a constraint problem where f and R0 are greater than or equal than 0, and C is in a box in a box, there is a box constraint on Psi, and these constraints comes from physical information a priori. Okay, so the algorithm in this case for this software is the following. So the computational framework is the following. We start from set the starting values for the parameters, and then there is an iterative procedure where the solution is found by solving this minimum problem using a numerical method, which is the Gauss-Seidel Gauss-Seidel method. And at each iteration, the regularization parameter is updated using the balancing principle that Professor showed you before, until there is a stopping criteria is reached. So passing to the software, this is the graphical user interface of the software. The software is freely available at this link, which is the link of the site of the Department of Engineering of the University of Bologna. And it is implemented on Windows and Linux system. So when you open the software, the first thing to do is to select the data folder and import the data. So by press this button, and there is a window that pop up where you have this the data that you can upload to the software. And okay, you can use this software also on your data, of course, but the important thing is that it's important to organize the folder of the data in a specific way, and the folder must contain 4 files. The first one is the Excel file where the actual data are present. So they are organized in this way. We have the first column where there are the frequency, there are no frequency. The second column, the relaxation rate, the corresponding relaxation rate acquired. And then there is the third column where there is the error. Then there is a file, a .par file, where you specify the name of the Excel file, the number of inversion points that you want to use, and the inversion time limits of the problem. Then there is another file where you set all the parameters for the numerical method. So, for example, the starting value of the regularization parameter, the number of the maximum number of iteration of the algorithm or the tolerances, and also the starting value of the quadrupolar parameters for the algorithm. And then at the end, we have another .par file where there are some flags for the algorithm. For example, you can choose to print the plot of the statistical analysis that you perform with the software, or if you know that there is the quadrupolar effect, you can directly set from this file the presence with a flag. So the after you select your data, on the left there is the profile, the experimental profile is loading on the left, is loaded in on the left. All these parameters, all those parameters that I told you before, you can control also from this directly from the software. So it's you can change everything also from the software. And when you run the inversion, after not so much time, you have the results. So on the right, you can see the correlation time distribution. So the f of tau c, obtained by the related to the linear part. There is also the fit of the profile, which is quite good in this case. And here on the top, on the right, there are the values of the quadrupolar parameters and the value of the R0 and all the parameters that you want to extract with this software. I reported also these results for other cases. So this is another cheese sample. You can see that the fit of the performed by this algorithm, this software is quite good. You can also have some statistical analysis and print the results. This is the residual, the histogram of the residual obtained by the software. And this is another example for a porous media. Also in this case, the software works very good, as you can see also from this zoom of in the part of the quadrupolar effect. And another thing that we implemented with the software is a uncertainty analysis based method where you can repeat the run of the software for a large number of data sets. These data sets are obtained following this equation. So we add random uniform noise in the confidence interval of the data, and we apply this method for an n time to extract n set of results. So in this case, we have 500 correlation time distribution. And of course, we will have also 500 values of the parameters that we extracted. So for example, in this case, I reported 500 values for R0 and the 6 parameters of the quadrupolar effect. And this is this can lead to obtain a confidence interval for these parameters in order to have more robust estimation of the parameters. So this was the first software. Then if I have time, I will show you also in practice how it works. But let's pass to the second one. The second software is called MovePen 2T, and it was developed to obtain the relaxation time T1, T2 maps. It performs on data acquired using conventional inversion recovery and CPMG sequences, where the signal has this expression. And the algorithm of this software is based on the multi-penalty regularization that you see before. So we have to solve this minimum problem. In this case, we have not just one regularization parameters, but n values of these regularization parameters. In this case, for this framework, they are locally adaptive parameters. The software, the graphical user interface of the software is quite similar to the previous one, and this software also you can download it from the same site of the University of Bologna. And it works in more or less in the same way, in the sense that you have to select the data folder, import the data. The data folder is organized having the 4 files that I told you before. Of course, the difference is that in this case, the actual data came from another experiment. So you will have a matrix with the ER and CPMG experimental signals. And when you load the signal, you have on the left the experimental signal, and you can run the inversion, and on the right you have the results. So here there is a T1, T2 map. On the top you have the values of these parameters that you extract. This I just reported the same results before. And also you can see the 1D distribution related to the 2 different relaxation time, so the projection of the on Y and X axis. So this was everything for the two software. Here I reported also some references for everything. And if I have time, I will show you also the execution of the software in real time. I don't know if I still have time.
You still have half of hour at least.
Okay. So this is the software, the first one, Model 3 FFC. So you can select data folder. You have here. Let's try with an example without the quadrupolar effect. So if I open this data, here on the left we have the profile, and there are no local maxima. And if I run the inversion, after few seconds, you obtain a lot of figures because I select to print everything. Here there is the fit of the profile, which is quite good. We have also the correlation time distribution extracted, the f of tau c, and all the information about R0, for example, here, the residual norm, the key squared, and also other information about the statistics that the software performs. If we change set of data, using, for example, Parmigiano cheese sample, let me close everything here. Okay. Here on the left, there is this new set of experimental data. You can see that the quadrupolar effect is present in this window. And if you run the inversion in the same way, after a while, okay, you obtain, also in this case, a good fit, as you can see in this part of the quadrupolar, and all the information, all the extracted parameters, so R0 and the 6 parameters of the quadrupolar in this case. As I told you before, you can also perform the uncertainty analysis based method that we developed, and you can choose from here the number of repetition by adding uniform noise to the data. Let's put 5 to be quick on the same set of data. And then at the end, I will obtain 5 sets of correlation time distribution and also the information about the parameters that we extracted. Of course, it requires more time in this case because I'm repeating for 5 times all the inversion. Okay. So we have this this figure 3, 5 correlation time distribution with the in the red we have the first computed one, and then the mean between the 5 of them, and in gray all these results for each inversion. And of course you can repeat this for a large number of times, but of course it will require more time. So this was the model 3. If I open the other software, it has more or less the same graphical user interface with, of course, different parameters. When you select the data folder, the data folder are more or less the same. Here there are more files because are the output files, but you can select this one. And okay, this is, maybe I will select another one, this one, okay. And if you run the inversion, at the end, you obtain the, these are some statistics results. You can obtain the T1, T2 map with the projection on the x-axis, so for the relaxation time T2, and the projection on the y-axis, with the values also printed here on the top on the right. So this was everything. And I finished my presentation. So thank you for the attention, and if you have some question, I'm here to answer.
Thank you. I would propose, because to my understanding, I mean, let me put it in this way. Is this something else what the Bologna team is going to present? Or you just, oh, this is the end of your lectures?
I think this is the end.
This is the end, you know, because I'm just wondering, as we do not have questions, maybe we have other questions?
Danuta?
Yes?
I'm sorry, I'm driving, but I was listening to the talk of Giovanni and
Yes.
Fabiana, and I have a question. I think it's a simple question, but I'm curious. Giovanni, when you present this distribution of correlation times, can we look at can we understand that the width of these peaks that you have for each one of the central correlation times? Can we interpret them as the uncertainty of those, correlation times somehow, or?
You are referring on this kind of repetition.
Yes.
Okay.
Yeah, I'm sorry. May I just be more precise? So if we try to make an analysis of the same data, but not using the concept of the distribution of correlation times, probably we will be driven to a solution which would have, I don't know, maybe the same number of correlation times, but not as in the form of a distribution but in the form of some discrete number of values with some uncertainty on them. So my question is that, can we look at this distribution and think on the width of these peaks as the uncertainty of those central values of those peaks?
Yes, I think that you can think this like the value of the correlation time with a confidence interval around of the this peak obtained by this repetition of the considering all the, let's say, all 500s or the large number of peaks that you obtain around the same peak, let's say.
May I have also a question?
Okay.
Adriana actually posted something. In this software, so maybe we could say it first. In this software, is it specifically to analyze RHH plus RHN in the case you have different contribution in the relaxation rates? Cannot you use this software? I mean, you can see you can read yourself the comment in the chat box, the question. Because I'm not sure I understand the question.
Yes, I don't understand what it means, different contribution.
I suppose it's like, let me put it in this way. You have, for instance, biological molecules, and you have those quadrupolar effects, which I'm going to talk about. So you have like proton-proton relaxation contribution and proton-nitrogen relaxation contribution. Proton-nitrogen contribution gives you those peaks, yeah? So I suppose that Adriana is asking whether your software takes it into account somehow. That there are proton-proton and proton-nitrogen relaxation contributions.
Okay. From my point of view, it is difficult to answer because actually what I see and thinking about the modeling of this problem, everything is related to the way in which I build the constraints. The constraint, the set of constraints in this specific, for this specific data that we have seen, were built in such a way that they could reproduce these types of phenomena. If I understand what she's saying, maybe changing the changing the components, we should change this the constraints, and in this case we can develop the same approach, but adapting the constraint to the substance. Of course, we don't have a universal software that solves every types of material. If we change, if I'm understanding properly, the material, we have to adapt at least the constraints. Maybe the approach is the same, but we have to adapt the constraints. This is as far as I can understand it.
I do not think it's a matter of constraints, because to my understanding, if you have a profile, you do not inquire somehow into the physics of the system, but so you do not consider the relaxation scenario, or you do not consider any specific relaxation models. You somehow try to decompose, sorry for the simplification, please correct me if I'm not right. You try to decompose the frequency dependence of the relaxation data into a series of Lorentzian functions with specific correlation time. And then you get a series of correlation times, and the correlation times somehow cluster, yeah? And in addition, the amplitudes of those Lorentzian contributions. So somehow the amplitudes give you the distribution, yeah? Like the populations of the individual correlation times, if I am right. So in principle, I could imagine that one could compare what you are doing with this very simple approximation, which I demonstrated yesterday. Namely, I decomposed relaxation data, not going into what they are. I only told you vaguely that this is like, I don't know, some hydrated biological molecules. And then I got 3 relaxation contributions associated with 3 relaxation third correlation times, which I called slow, intermediate, and fast. And if I would take into account the amplitude, the dipole-dipole coupling constants, I could create a kind of distribution of correlation times out of that in a very, very, very simple way. So what I think, to my understanding, you just apply to some extent the same approach. However, you do not limit yourself to 3 contributions, but just whatever comes, yeah, whatever is needed.
Yeah.
However, is it so?
Yes, it is so. But in the problem here is that there is no unique representation of that. I mean, this transformation is not injective somehow. So you can have different types of distribution that give you the same, let us say, profile because of this type of kernel, because of this type of transformation. And this is the reason why if we change we add constraints, we change also the way in which we, for example, we sample our distribution times, we can have different clustering. This is the problem.
Well, this is one side of the problem, but this is how to say something which one cannot avoid, I suppose. This is like, whether you can get unit feed. However, what we have a problem with is that our relaxation effects, which influence the shape of the relaxation data, but they have nothing to do with motion. For instance, if you have, like Adriana pointed out, proton-nitrogen dipole-dipole interactions, but this is not only this case. They give you the relaxation maxima, relaxation peaks, which have nothing to do with motion. So if you apply your approach, your software will be trying to reproduce them in terms of Lorentzian contributions associated with some correlation times. So we will get a certain distribution of correlation times, but this will be not true because the system is not performing any kind of motion. Actually, the peaks stem from something else. Actually, I would say that in contrary, if you have such peaks, it means that you do not have motion, or you have very slow motion. So it is like a fraction of, you have, for instance, a fraction of immobilized biological molecules, and this fraction gives this effect. So somehow, this is completely different phenomenon. For instance, also, if you have paramagnetic systems, you have several other interactions, and one may not describe the relaxation data in terms of Lorentzian function. Moreover, if you have, for instance, paramagnetic systems, even if, for instance, like, you know, for this case which Pedro presented, for the solution of manganese ions, this is a very simple paramagnetic system. In fact, it can be described with some approximation in terms of Lorentzian functions. However, the functions must be taken at different frequencies, not only at the proton frequency, but also at the electron frequency, which is like 658 times higher than the proton frequency. So it cannot be just like decomposed into Lorentzian functions taken at the proton resonance frequency. And we are just worried that the distribution of correlation times is affected, but not taking into account all those quantum mechanical effects in the relaxation scenario.
So it is a problem of model.
Yes.
It is a problem of model. Of course, given a different model, we have different solution actually. This is a software for this model, for what actually can be obtained by a model like this. Of course, there might be there are other models, and
yeah, but maybe one should be aware at this stage that actually we can apply your model in cases when the proton relaxation contribution is the dominating relaxation mechanism. Which is, well, yeah, quite often for food. What do you think?
Danuta?
Yes?
I'm sorry, I lost somehow my connection, so I apologize. I was listening,
Fabiana
and I want. Now it's Fabiana. Okay, I was wondering if somehow if we think about this relaxation enhancement caused by cross relaxation or the paramagnetic relaxation enhancement, which are well, at least two cases where the relaxation rate increases in certain frequency ranges with respect to otherwise regular background curve, I would say that probably the background curve could be explained most of the time by a sum of Lorentzians, and only this,
yes.
Enhancement area, I mean, areas of enhanced relaxation would have to be extracted obtained or calculated or estimated, not using this distribution of Lorentzian curves.
Yeah, but we are thinking about a kind of limiting case. The peaks are very sharp and you somehow can take them out, but there are cases between, there are like...
Yeah. Yes, of course. The case of this gadolinium, or even the cases I presented yesterday with iron and all that, this broad relaxation enhancement in the high frequency region clearly are broader, and they come out of. They are clearly seen above what we could imagine a background curve underlying this behavior. I don't know. It's just a comment. Sorry.
From my side also, because I think it's a really great approach, but I think we should test what happens if we have other relaxation contributions. I mean, how the software interprets that.
Yeah. On my side, for what I can understand, because I am not a physicist perfectly, but surely there are, the experiment should limit the usage of this approach. I mean, this approach is not universal, and it would be interesting to understand where and to what extent it can be used safely and where are the limitations. And these are the people who know the problem from the physical point of view, from the material or quantum mechanics point of view, can give us somehow the bounds on which this approach can be applied safely. What I see is just how to take in this model from give a proper solution which is let us say correct and makes sense, but just related to the data feed and to the type of information that we can extract from the distribution. I think it's something that should be tested from people that make use of this use this software or tools like this to obtain properties of materials, properties of different phenomena. And I agree when I say, I heard someone saying also in this context that the important thing is to use different approaches and compare different approaches and see how in a given situation different types of model can give us information about some physical phenomena or some physical motions or dynamic information or about the dynamics of the process. I don't know if I'm right, but this is my observation. Let us say somehow from outside, because as I say, I'm not a physicist, so maybe I don't properly capture the physical meaning of this phenomena.
I will put it in this way: what we should do definitely is to come to Unibo using our project and make this brainstorming. This is what it is for.
Yeah.
It's
Yes.
great that we have this kind of approach. It's very unusual, and I think can be very, very important for this kind of applications, because it can give a kind of characteristic fingerprint of the distribution of correlation times, characteristic for specific food products. Well, do we have more questions? If not, thank you so much, and I announce our break. Thank you.
Okay, thank you.
Thank
Bye.
you.
Bye, everyone.
Bye.